Rosario Atanasio is all about making things spin and doing it with purpose. When he's not out spinning the wheels on his bike and setting record course times all over northern Illinois, he works at STMicroelectronics as an applications engineer, designing some of the most sophisticated motor drivers in the world. Is that how he's been getting around town so fast on his bike? We may never know, but today he's here to share some insight on how you can more easily prototype and scale your motor control applications. Welcome to Tech Chats, Rosario.
Hi, Chris. Thank you, and very happy to be here today.
So, what are some of the trends you see in the market?
So there are many driving forces that are contributing to a real revolution in the power conversion arena. These driving forces are mainly efficiency, power density, and reliability. And more specifically, in the motor control field, we are seeing the adoption of integrated motor drives. The main objective of integrated motor drives is to make the drive electronics sufficiently small and rugged so that it can ideally be fitted into the housing of a motor. Now, if we look, for example, at the center part of the slide here, we see that we are proposing three different types of architectures that can be used to implement an integrated motor drive. Let's start from the architecture number one. This is also what we call a discrete solution. In this architecture, we have a separate MCU, we have a separate control logic, separate drivers, protection, signal conditioning, and the power management circuit, as well as separate power switches. This type of solution is very flexible and can be easily scaled in power from low to very high. There are also some limitations. The main one is that the number of components in the bill of material is quite high. And the second one is the space that all these components require on the PCB is quite big. So there is actually a better solution which is shown by architecture number two, the one in the red box. Here basically we bring inside one package the MCU, the control logic and the gate drivers, as well as the power management and the signal conditioning. So we realize what we call a system in package or an SIP. This brings several advantages. The main one is a smaller form factor compared to architecture number one, and also the possibility to scale in power. In fact, if we look at this architecture, this has external power switches, and this means that if I wanted to increase the power of my application or increase the input voltage, I can eventually pick from different part numbers of FETs, IGBTs, or silicon carbide FETs, from, let's say, very low to very high voltages. So this gives a good degree of flexibility and freedom to the designer. The other very important factor that I wanted to highlight for this architecture is the possibility to optimize either for efficiency or EMI. In fact, we have external gate resistor networks, so I can change the resistor values in order to shape the fronts of the turn on and turn off transitions, either because I want to optimize the efficiency by making them faster, or I want to slow them because I have some EMI issues that I needed to cope with and I needed to resolve. So scalability and a certain degree of flexibility are definitely the main points of this architecture. And finally, I wanted to point out the architecture number three, which shows the integration into one module of the power switches, some of the control logic, and the gate drivers. The main advantage in this case is the highest integration level that can be achieved, because these are the components that actually require the most space on the PCB. But these advantages come with the cost of lower flexibility. In fact, I can not anymore work on the gate resistor network because this is also embedded into the power module. And therefore, if I have to optimize or fine-tune my application for efficiency or for EMI, I may have more difficulties. So if we look at low to medium power kind of applications, architecture number two is the one that probably provides the best advantages in order to enable this revolution that I mentioned at the beginning, where efficiency, power density, and also reliability are the main driving factors.
What do designers gain with the system and package approach?
So first of all, I would say that the main advantage is power density, because having a device that integrates so many parts of the system into one tiny package helps to minimize the space required on the PCB. And it also simplifies the layout for the designer, because most of the routing is already done inside the IC. The IC also embeds high performance gate drivers, which are able to drive both the high side and low side device. We have an advantage of maximum efficiency, because the power management is done inside the system in package. Also, because we have a 32-bit microcontroller based on the ARM Cortex M0 technology, we have the possibility to implement complex control algorithms. Also, we have the possibility to include accurate control or decoding logic for the control of a motor with all effect sensors. Again, something that simplifies the final implementation. And last but not least, I would say again, scalability is one of the advantages, because by selecting the right product inside the STSPIN32 family, it is possible to have the right analog resources that perfectly fit the application from a cost and from a performance point of view. And it is possible to keep the same M0 core, which means I do not need to make big changes to the firmware, which ultimately would require a lot of engineering time.
You've mentioned scalability a couple of times now. Why is that so important?
Yes, scalability is really important in the current market scenario, because it allows the shortest time to market. On top of that, there is also the need to adapt and capture different market trends. In fact, if you wanted to scale up or down your application, you can just select the different STSPIN products. For example, let's say that the designer has developed a low voltage application and now is asked to work on a project where there is a high voltage bus, for example, for home appliance applications. It is possible to switch from a low voltage STSPIN32 to a high voltage STSPIN32. Mainly what changes is the type of technology that we are using, which affects mainly the gate driver.
So, how would someone design a motor control application that they can scale?
Yes, so to design a scalable product, the first step would be to pick the right product within a certain product family. And this is probably the most important task, definitely not a trivial one. If I had to design a scalable product, I would start from a product family that would allow me to design both the low voltage and the high voltage application. I would want to have a device that can cover multiple controller strategies, so that, let's say, a powerful enough core and MCU. I would also like to cover multiple motor technologies. And finally, I wanted to have a variety of the tools that enable faster prototyping and proof of concept. And if I look at the three-phase gate drivers, in particular, the characteristics that they should have, probably the list here is even longer. I would start from the gate current capability, because for a product that needs to be scaled up or down, it is very important to adapt the gate driver current capability to the type of device that I'm using, and to the figure of merit of the device. And the other really important thing is, I think, especially important as the power goes up and also as the voltage goes up, is the ruggedness of the gate driver. And here in particular, I'm referring to the scope capture on the right-hand side of the slide. What I want is a ruggedness against the below ground spikes. And as you can see here, we have over 100 volts of below ground spike. For scalability, of course, I want also to cover a wide range of both indoor and outdoor applications, as well as operation in harsh environments, so minus 40 to 120 degrees C is definitely a plus for this type of system.
What's the breakdown in applications between low voltage and high voltage products?
There are several key applications where the low voltage family can be used. So first of all, let me say that there are three products in the low voltage family, and these are the STSPIN32 F0, the F0A, and the F0B. And the difference between these products is mainly in the number of internal op-amps, comparators, and the GPIOs. Then, in terms of the key applications, we were very successful with this device in industrial automation with battery-powered power tools, small battery-powered home appliances, fans, drones, and robotic applications in general. The main benefits of the low voltage family are, beside the integration which we have already covered, the full compatibility with the STM32 ecosystem, the support with the firmware library of the 6-step modulation and the FOC, both censored and censored, and both censored and sensorless, and the availability of a very extensive ecosystem for faster design. If we look at the high voltage family in a similar way, we can cover many applications. In this case, still targeting power tools, but supplied by higher voltages. For example, 36 to 120 volt DC is the most common range. We can also target offline applications, for example, air conditioning, industrial fans, or let's say in general, industrial automation applications. Here, the advantage of this product family are again the compatibility with the STM32 ecosystem and the support of the main control algorithms. So we can pick in the family devices with different source and sink current capability. And another really important point to highlight is that all these devices are pin-to-pin compatible. So if you needed to scale up or down your application, or you needed to design a different product, you can still use most of your hardware and just change the main components which go together with the STSPIN32. In this way, we can basically realize a very compact, flexible solution, and we can offer faster design and faster prototyping thanks to the exhaustive ecosystem that we offer with these devices.
You mentioned that one of the benefits is access to the STM32 family or the STM32 ecosystem. What's that mean for motor control applications?
Yes, we have developed a complete ecosystem around these product families, and this ecosystem is basically a mix of development boards, firmware, software tools, and also documentation. The board, for example, boards can be divided into general purpose boards and application specific boards. So if I look at the Stival STSPIN3201, this is a general purpose demo board that implements a 3-shunt topology and is supported by a field-oriented control library. We have already talked about the firmware packages. So we have, let's say, both censored and sensorless FOC, or censored and sensorless 6-step modulation. And then we have a very nice and flexible software tool, which is called the Motor Control SDK, which also integrates the Motor Control workbench. All of these firmware and tools can be used with standard development environments, such as the one provided by IAR system or Kyle, or even the STM32 Cube IDE, which is from ST and can be downloaded from our website free of charge. Similarly, for the high voltage ecosystem, we offer 4 boards. The first one is the EVAL SPIN 32F0601S1, which is a single shunt topology with the high voltage STSPIN 32. The gate drivers here are rated at 600 volts. The same board is offered in the 3-shunt topology, and it is also offered with the F0602, which has a higher gate drive current capability. And finally, we have another single shunt topology, the EVAL SPIN 32F0251S1, which uses the 250 volt STSPIN 32. Similarly, the Motor Control SDK is the main tool to use together with these boards in order to spin a motor.
So what exactly can a designer do with the motor control workbench?
The Motor Control Workbench is a GUI that is a part of the Motor Control Software Development Kit. This GUI allows the user to input all the parameters of the application. And once we have defined all these parameters, we can generate the code, and this code can be also imported into the STM32 CubeMX tool. The other important thing to highlight is that there is a monitor interface. This monitor interface allows to check the rotational speed of the motor, check if the the application runs into a fault and what kind of a fault it is present. It also allows to tune the PI parameters of the application, which is another really important feature. So overall, it is a very powerful tool that reduces the design effort and the time that is needed to spin a motor.
And you had a couple of dev boards that you wanted to go into detail on. Tell me about those.
Yes, so the first one is the Stival ESC002V1. This is a very compact solution that we have realized with the drone applications in mind. As you can see, there is a form factor of 50 by 25 millimeters. The top side of the board has basically only one IC, which is the STSPIN32F0A, plus a number of external components, which are mainly resistors and capacitors. While on the bottom side, you can see the FETs, which are, in this case, strip FET F7 low voltage power FETs from ST. They have 4.5 milliohm RDS-on, and they come in a power flat package, which is ideal for very compact layouts. So this is a very small, compact design with a maximum input voltage of 30 volts and a maximum current of 20 amps. So if you think about the size of the board and the current and the absence of heat sinking, you can really see the value of this application. If we look at the high voltage examples, here is that we offer two options. One is rated for input voltages ranging from 25 volts AC up to 175 volt AC, and it can be used both with the 6-step algorithm or the single shunt FOC. The power stage can be implemented with either MOSFETs or IGBT in multiple package options. For example, here we are showing the DPAC, but this board can also be mounted with power flat 5x6 packages. So it's a very flexible platform that again suits very well the purpose of scalability. In summary, I would say that the STSPIN32 family has several advantages. The most important ones are the high integration that is provided by having a system in package. This provides very important advantages for power density and efficiency. The number of components on the board, as we have seen, can be drastically reduced, and efficiency can be very high thanks to the onboard power management unit. And the devices are also designed with the reliability and harsh environments in mind. Finally, the system is provided with a very compact package. It is in fact a QFN 7x7 millimeters.
Thank you, Rosario, for sharing your time with us today. Once again, that's Rosario Atanasio from STMicroelectronics. If you'd like to learn more about the ST Spin family or maybe take it for a spin yourself, click the links in the description or visit Mauser.com. And be sure to check back soon for the next episode of Tech Chats.